on the Earth or anywhere, or on other planet also, or it is a reflected signal, say we like a sensor like a LIDAR, where we transmit a signal, it goes to the Earth or the target, and some return signal comes back, and we try to sense that, where the signal strength will be high. So such sensing is also done in different frequency ranges. So that is optical remote sensing. And then as I mentioned about radar, radio detection and ranging. So all these microwave frequencies starting from what we call VHF band up to now what we call millimeter or sub-millimeter band, wave band, where it goes up to frequency up to 500 gigahertz or 600 gigahertz. So from almost 500 megahertz to 600 gigahertz, that is the band which is covered mostly, which is the microwave and the millimeter wave spectrum of our frequency spectrum. And basically the radar is the main sensor in that. And how this radar or any other optical sensor, what is the basic principle behind that, that I will come. So basically remote sensors are of two types, passive sensors as well as active sensors. Passive means you try to find and collect information which is naturally emitted by different targets and try to analyze what is the target. So you have water, you have soil of different structures, you have rocks, all these things you can analyze from the natural emission of the signals, and also man-made targets also. So it is not only natural targets but man-made targets. And there is other category, active sensors, where we carry our own source of illumination. So in the passive sensor we are dependent on sun. So whenever sunlight is there, sunlight falls on the targets on the Earth or in any other planet, and whatever signal comes back from that frequency spectrum, we try to analyze and try to find out or classify it or characterize it. But in the case of active sensor, as I mentioned, different frequency bands, so I will carry the source of my interest. Say if I want to do mapping or what Vice Chancellor Saab was mentioning, different bands. So if I have a sensor in C band, I will carry a C band source, a magnetron or a amplifier, which I will carry in as a part of my satellite or aircraft or on a ground system. So I can use that source, transmit a signal, that signal will go somewhere, some part of that will strike that target, and some out of that something will get absorbed, something will get reflected, and something will be returned back to the source from where it has been transmitted. So all these things comes part of an active sensor in both optical as well as microwave. So this is how it works. Basically you have an antenna or optics, your lens, like your camera works. So basically in a passive sensor you have an antenna or optics which receives signal, because it is basically a passive system. As I mentioned, depend on sun as a source of illumination. Something gets emitted naturally, and that is received by a very highly sensitive receiver. You can imagine, because whatever signal is coming back in case of passive sensor is a very weak signal. So you need to properly sense it. So your sensitivity has to be very high for such type of receivers. And then finally you digitize them, because nowadays everything, all work is being done digital domain only on computers or any other microprocessor controllers. So that is the digitizer and processor part of it. You process, you analyze, and then come out with the final application for which all this has been done. And then what is active sensor? As I mentioned, active sensor means it will carry its own source. Source means any transmitter. It will transmit a very high power signal, because as I mentioned, passive sensors has to detect very low signal. While in case of active sensor, because there is also natural emission, and then we are targeting a particular range of interest of our frequencies and characteristic which we are looking for. So we need what you call a very high power transmitter, because these are being carried in a different altitudes. So you can carry it in an aircraft, or you are putting it in a satellite which is moving at a orbit or a height of 500 kilometers to up to 1000 kilometers. Then you can imagine a source which is there at the height of 1000 kilometers, it is transmitting something, and something goes to the earth and then comes back. Only a portion of that. Everything doesn't return back. So you need a very high power source. So if you calculate theoretically, I can give you example of a radar system. If I want to characterize or find out some signal or a vehicle, like a car or a truck or a railway moving on the tracks on the earth, and I have a satellite which is orbiting at 600, 800 kilometers, and I want to image those targets, and we have been doing that regularly. if you do only simple calculation by your law of physics or theory, you will come with a requirement of power in the range of more than 1 to 10 megawatts. So now you can imagine, then you have to put a nuclear reactor in a satellite or aircraft to meet this requirement. And that anyway, naturally, it is not possible. Then how it is done? So there is what the ingenuity or the science part comes, technology comes. So you try to modulate the signal, you try to find out different ways and means by which you can do that and achieve your desired goal within a reasonable amount of power. So generally this power will be in the range of starting from some few watts, say 5 watts, up to say 4,000 watts. I will show you an example of this radar imaging satellite what I was talking about. It is carrying a source of 4,000 watts. So up to 4 kilowatt, 4, 5, up to normally people have achieved up to 10 kilowatt of power you can carry a transmitter on board on a satellite or aircraft. So from 10 megawatt we have come down to 10 kilowatt. So you need the 1,000 time improvement. So how you have done that 1,000 time improvement? That's where technology comes into the picture. Your design capabilities, your ingenuity, your intellect, all these things is utilized. So to coming back to this 25 years, as I was mentioning, we started very early, as I mentioned, in 1978, it is mentioned here. This was our first actually remote sensing satellite, but since it was an experimental satellite, otherwise we have spent almost 35 years, you can use it. So 35 years we have been working on these satellites, remote sensing satellites. But what was the first one, right now we are celebrating is this IRS-1A. It has completed 25 years of service. Of course, that satellite is not working today because any satellite has a life of 5 to 7 years maximum. They are designed, earlier it was when it started, it was designed for 3 years, but it worked for almost 8 to 10 years. So that was the achievement for ISRO. So like that, but that is being replaced by, say, 1A was replaced by 1B, followed by 1C, 1D. So we have a series of satellites, remote sensing satellites, because that's why we call it operational services. So user should have continuity of services. For that, we have planned out all these programs so that there is no gap in the user requirements. Whenever they want any data or image or anything else, application requirements, we are meeting that. And for that, the total program has to be planned out, and that's what we have done. So this gives you the total scenario, and we started with optical sensors. All these are optical sensor, and then that was followed by various, this was the first microwave radar sensor was put here along with the optical sensor. And these are again were optical sensors, and recently these megatropics, and I will talk about the radar satellite. So you can imagine that we have started from a imaging resolution of 1 kilometer. That is, I'm carrying, as I mentioned, a sensor in a satellite. It can image only a 1 kilometer resolution or accuracy of 1 kilometer. What does that mean? That a 1 kilometer area will appear as one dot in your final image. So say like this campus is some few kilometers of area, it will come as 4 or 5 pixels. So I cannot work out where is your Department of Physics or where is this hall situated. But now today we have systems which can cover up to 0.81 meters. So now you can imagine, I can see a vehicle moving on a road also I can track. So that is the capability we have. Space is same, my satellite is same. Satellite where it is orbiting, that portion is also same. But what has improved is our understanding and our technology and our science part of that. So with all that we have achieved, as I mentioned, now we can detect any target, and for all our security as well as any other application, we can do this imaging, and remote sensing has helped a lot in doing that. And then there are some problems with this optical remote sensing, like you have cloud cover, or you have rain, or that sun is not visible. As you say in Indian, all our border areas or most of the northern India, we have this problem of cloud cover. So in that case, how do you do imaging? Even though satellites are there, our sensors are there, but we don't get good images. Like you take a picture with your camera system within a fading sunlight, what will happen? That picture is blurred. Something similar happens here. So how to overcome that? For that only radar remote sensing or micro remote sensing has evolved, and I will show you how it has overcome the problems. So this was the 25 years we are celebrating today and tomorrow. So that was the first operational satellite launched from then USSR, that is Baikonur aerodrome. There was a Vostok rocket was there, which was utilized to launch this satellite, and it was operating at a height of 917 kilometers, and it could take image. As I mentioned, our experimental satellite started with 1 kilometer resolution images. This one was the operational one, which started with 70 meter and 35 meter almost. So this was the model, actual model of that satellites. And in fact, I can tell you this was a model of that actual satellite. What went into space is another one. At that time, when we were beginning all these activities, 25, 35 years back, we used to make one model of the satellite which was rigorously tested on ground. And then its duplicate model, or the actual model which is to fly, that was not tested that rigorously. Because in space, if you stress anything too much on ground itself, you have a doubt about its reliability working in space. So that we have worked out different space qualification guidelines, as we call it, reliability aspects, other things. Because anything can work on ground, and even ground it doesn't work. If something fails, we can always repair it. As you know, mean time between failures and mean time to repair. It is always under your control. All these are maintainable systems, whatever you have here on ground. But in space, once launched means gone. If some problem occurs, then you have to close that mission only. So if we don't want that scenario, what to do? So for that, as I mentioned, you make one model which is rigorously tested, it undergoes different testing, and then finally it's another version which is tested to a lower level. That only is because you have now proven your design, it will work. So that's why you don't stress it too much the next model. So that was how we started. But why I am telling all these things is that nowadays when we have to launch 2, 3, 4 satellites per year, we cannot afford this. This took almost 8 to 10 years of development. We started in almost 78, 79 and launched this in 88 and made 2 models of that and then launched the final model. So that sort of luxury is not there now available to us today, because if you have to launch 4 satellites and for each I go on making 2, 3 models, it is impossible. We don't have that much resources. Even economically, it will not sound that economical. And anyway, that resource is spending all those efforts, all these not required. So you can, that shows our now confidence in building satellites. So that is also a big achievement. And we've released a stamp also by Government of India. So this is a satellite which worked very well. Its design life was 3 years, but it worked for almost 8 to 10 years. So this was how the capabilities, I already told about that. We started with 1 kilometer and today we have gone, this is a different series. We initially 72 meters, then 188 meters wide. You may be wondering why there is 36 meter and then why you need 188 meter resolution images. Because there are different applications. I will come to some of the applications. Say like agricultural field, where you want to cover vast area. Say whatever Indian area is there, our subcontinent area, if I want to cover very fast, because these satellites are polar satellites. So they are moving from north to south as a almost 90-degree type of rotation. So if you want to cover full India, it will take almost 22 days. So how to cut short that? So in that case, what I have to do, I have to compromise resolution and increase my coverage area. So that's why how this 188 meter and I have a wider coverage. So that has come from that. So we have all types of sensor in same satellite. So you can operate it in different modes, and at the same time you can have good resolution images also, and you have a coarser resolution images, but which is covering wider area. So that is our journey for first 20 years. And then as you can see now, we can go less than 1 meter images also. So a moving truck or a moving vehicle on the road also can be detected with these images. You can see all these Palm Beach and all these images which are being shown by different satellites, 5.8 meter, 2.5 meter. This is the actual sensor camera, like we have your own camera nowadays, CCD cameras and everything. This is the camera which are being put in satellite to do this type of. These are the other 3 categories. This is that wide field sensor which has a coarser resolution, but it can cover a wider area. So that's a different categories. Like here you have from 5.8 meter to 56 meter. And 3, 4, whatever is written is the 4 bands. So you can, how you get a color image? You take RGB like the red, green, blue. So you get information in different bands and try to put it as a false color composite, and that way you generate a color image. Now coming to, that was optical remote sensing. Now coming to microwave remote sensing. As I mentioned, radar is a basic sensor, and in fact, you must be wondering that our first radar satellite, which is truly a technology marvel, that was launched only in 2012. But interestingly, we started working on micro remote sensing also in 1978 when we started working on optical remote sensing. So you can see how much time it took to mature. Basically, what I am trying to convey is what are the complexities involved in that, the money involved in that, because everything is a part of all these things. So that resulted into all this time which we have spent, efforts we have spent, technology which we have mastered, and today we have a plethora of all satellites which are in space in different categories, different bands, from C band to Ku band to X band. And this is the satellite which I was talking about. I'll show you a brief glimpse of all that activities. And then we have an airborne radar system also. And this is the antenna of this satellite which is shown. So this way we have worked on different applications. So like this OceanSat, I'll show you details about that. This OceanSat scatterometer, this is utilized to measure ocean surface winds. So whatever winds are blowing over ocean, that can be measured from a satellite, and this information can be relayed to all the ship navigations as well as fitting into our meteorological models where we do the weather prediction. So because wind speed over ocean is a very important element that decides, in fact, many of our weather conditions in India, especially tropical countries like India, are prone to all sorts of vagaries. So basically what a radar sensor is, as I mentioned, it is basically the resolution is decided by this signal which you transmit. So the bandwidth of the signal will decide the resolution with which you can image a target or any ground surface. And similarly, in any image if you want to generate, you have X as well as Y direction. So Y direction is again decided by the geometry of the signal. So this is how that geometry I have shown, and you transmit a what you call a linear frequency modulated signal. Instead of a sine wave frequency signal, you transmit a modulated signal. So that's what I was mentioning about the power requirements, with how I manage with a low power and still achieve better sensitivity. So that is taken care by this modulating the signal. So that is an example of how we do the linear frequency modulation signal. So this is the basic principle. And this, I will now come to that radar imaging satellite, which is now completing almost 1 year in this April, and it has worked flawlessly for all the activities. And I'll show you how this imaging takes place, because in a pictorial form, you can click on this. So this is how the satellite is moving. You have an antenna which is transmitting a signal, so that beam is formed. As satellite moves, you cover a strip of a signal. So this is how it is covered. So what you get a return signal, you have to process it, and then you get an image like this. So basically, it is called strip map mode because you have a continuous strip of ground which is being imaged continuously. When a satellite moves, it gets a signal in X and Y direction, which is it needs a very complex processing on board as well as on ground to derive and generate this image which is of 3 meter or 6 meter or 20 meter resolution. So similarly, we have different modes also. So strip map mode will give me 3 meter resolution. So if I want say 1 meter type of imaging, I have to go for spotlight mode. Similarly, as I was mentioning about wide area coverage with a poorer resolution or coarser resolution, then I have to go for what we call a ScanSAR mode. So these are the different modes in which this radar will be operating, and all these things is commandable. So you have this radar operating at a height of 536 kilometers. It transmits signals in various different modes depending on the command which is given from ground earth station to this radar, and then accordingly it will carry out the imaging in different modes, and you get images of different resolution as well as different area coverage. Next. So this is basically the hardware configuration of the system where we have, which is amenable for all these multi-mode operation. I will not go into much detail of that because it is a very hardcore technology part of that. The basic idea is that you have like your computer, you have what you call a payload controller. So which will interface, whatever ground commands come from here, it will go to spacecraft controller, and from spacecraft controller it will go to this payload controller, and based on that information, it will try to configure this signal in particular mode. Because as I mentioned, it is a multi-mode radar. So in which mode to operate, how to operate, all this commanding is being done through a telecommand from ground. And everything is being done automatically. So this was also one of the basic feature of this, that all operations were automatic. Once you command it, you operate in this street map mode, it will automatically configure different parameters, different data signals which are to be passed to different subsystems, so that it will decide on its own and then accordingly configure the whole system. So that was the basic principle behind this hardware. And this you can see, this is the satellite finally. Here we are showing the launcher, how it is stored for, because if you see a satellite finally in orbit, we will have solar panels. Any of you are aware of the satellite system. You have solar panels, you have different electronic circuit of spacecraft inside this cube. And then you have this big antenna, which is 2 by 6 meter antenna, which is actually deciding the imaging geometry and that signal which is being transmitted and received. So now if I want to put this satellite in a launcher like our PSLV launcher, you cannot insert it inside it. So you need to have, because that equipment bay volume is limited. So what you want to do is that you have a foldable system basically. So solar panels are also folded, this antenna also will be folded over one another, and finally it will be stored and put into a stored condition inside this equipment bay. And finally after the launch, you need to do all these maneuvers to deploy them. So that itself is a basic, very challenging task. If any of this thing doesn't get deployed, say solar panel doesn't get deployed, then you cannot generate any power, your mission is gone, because it cannot work without power. Because most power is derived from solar energy only. And you have a battery backup is there, where it takes care of eclipse periods. So these are the specifications. I will not go into much detail. Basically, this is a C-band, 5.35 gigahertz. It's the band in which this system was working, and it has a very big antenna. This antenna which is being seen, I will show you the details also. And that whole configuration, as I mentioned, you have in your computer or your standard desktop PC or a laptop, you have only one processor or a multi-core processor nowadays. You have multi-core processors working, but basically a single chip. Here you can imagine I have 314 microprocessor or controller similar to the one which is being there in your PC, working together in a synchronized fashion. See, if they doesn't work in tandem also, there will be problems, because I have to control and mobilize almost 576 antenna elements which are sitting on that antenna, and these are all controlled with this 314 microcontrollers or microprocessors. So each will have its own software written, which is rigorously tested and then put into that. So it has to ensure that this works reliably for its total period of life. So all these things, this hardware has to work, that software has to work, and depending on different telecommand modes, because as I mentioned, it is a multi-mode radar which has various configurable parameters. So it has to pick up the correct parameter and work. So if all of these 576 elements, they take up different parameters which are not in synchronization with the actual requirement, you have a total chaos. So all these things are avoided by this hardware in a synchronized manner. So that also was a unique feature of this particular satellite. And basically the genesis was that in 2000 we started this program, and as I mentioned, we took almost 10 to 12 years. How a big project is worked out in organization like ISRO or Department of Atomic Energy. I'm just trying to highlight that features. That first we start from the grassroots level. As I mentioned, ISRO is working for all civilian societal applications, whereas Sir was mentioning we have disaster monitoring or flood mapping requirements, you have agriculture requirement, you have forest, deforestation is our major problem in India, almost everywhere in the world. So how you take care of that in a basic level and use space to harness all these resources and work out a methodology that you will be able to meet all these applications. So we have basically what you call three major application areas. Land resource application, where agriculture, forestry, all these things, disaster management comes under that category. Then you have oceanographic application, as I mentioned about oil slicks or ship navigation, ship movements going over different parts of the oceans all over the globe. And then you have what you call high resolution applications. Of course, strategic applications in our border area, that is one requirement. But apart from that, high resolution imagery is also useful for change detection. So you have some, even now people are demanding why not earthquake can be detected using that. You have very small waves coming with there are precursors before earthquakes, as everybody, many of you are aware of. So whether we can detect that change. Right now we have not reached that level where we can do that measurement of L or S band of that S waves which are generated during an earthquake. But still, even in the other application areas where change detection is very important, or you want to measure height of terrain or height of the different areas where you are doing the mapping, that also will need a very high resolution imaging working in a differential mode. So with all this, first we set with all the real requirements, all the application scientists, what are the requirements to meet these societal goals, and then worked out in a backward manner and worked out the specification of this radar system. So that's why these multi-mode requirements and everything came from that only. It was, if I want to meet all the requirements of all the users, I will end up with a very complex system, but we took the plunge. So as I mentioned, how all that churning went on, and finally we took almost 1 year to decide on which frequency. See, now another point is that all these applications which are listed here, all of them need different type of frequency operation. So you need C-band operation, somewhere you need KU band operation, that is you have a 5 gigahertz signal requirement, or you have a 50 gigahertz signal requirement also. How you match them so that you end up with meeting most of the applications. Of course, there will be some applications which will be left out because that band doesn't support that. So all this is taken care by doing a rigorous, what you call optimization, or what you call a compromise choice. So basically, finally we decided that C band or 5.35 gigahertz, that band will be the optimum band for this particular satellite. And you can imagine what the complexity of the system, that you have this 6 by 2 meter antenna which is to be folded and put into the satellite, and it will have 1 by 1 meter such 12 structures. So, and in each 1 by 1 structure you can see how much electronics and cabling and assembly is going on. So you have almost here 24 computers, with what I was mentioning, on one tile. So such a way 24 into 12 means 288 as microprocessors are sitting on this particular tile or antenna itself. And then if you want to do cabling between different parts, you can imagine how complex and elaborate it is working out to be. And even if one signal or one cable fails or it is not connected properly, the system will not work. So you can imagine if I have to make such 12 things, put them together and make them work in space, not sitting on ground. That is the amount of complexity and precision required in this particular work. So these are the different way we have, after manufacturing, how we assembled the whole system. So as I mentioned, each 1 by 1 tile was assembled. So this is outside after this. So it is first to be tested. As I mentioned, it is to be folded in a satellite and put like this. And whether after folding it, when I do the deployment, it will work properly or not, that is to be first tested on ground. So all these activities were carried out like this, that here it is an undeployed state, I stored it, then I put it inside a thermo-vacuum chamber. So all this measurement also needs to be done in a thermo-vacuum environment, because as you know, in space there is no atmosphere. So you don't have air, you don't have anything. So in that thermo-vacuum environment, where temperature will rise up to -55 to plus 125 degrees centigrade, that total range you have to qualify your hardware or all the system. So for that, all this testing required is to be done on ground first, because then only you can say it is going to work reliably in space. So for that, all this testing has been done, and this is what is being shown here, that it has passed through all these stages. Almost it took, we sent our payloads from Ahmedabad, this payload was made and to send to Bangalore for integration with the actual satellite. So it took almost 1.5 to 2 years to pass through all these stages and declare that it is now worthy of going into space. So you can imagine the total power requirement, as I was mentioning, for different modes. It is maximum 4,000 watts of power. It is 4 kilowatt of power generation unit is sitting inside the satellite for this particular radar itself. And the total weight, if you can see, 930 kg. In fact, this was the heaviest satellite. Total satellite weight was almost 1858 kg. And out of that, 50% was this payload. Normally, in a satellite ratio is almost 30-70. Only 30% is your sensor or the payload, and 70% is other satellite parts, because finally satellite is a critical element which has to run continuously for 24 hours. But here almost 50-50, so we impressed upon the satellite team to reduce their weight and other volume and power requirements so that we can accommodate this sensor requirements. And this was finally how this payload was, as I mentioned, I was mentioning that years. The 2010 we flagged off this payload along with antenna, and then spacecraft was sent to our launch center. So it took almost 2 years to do all this testing, assembling, integration and everything to meet all the total reliability requirements. And this was how that if you want to test such a huge structure, this satellite or a payload, there also it needs special arrangements. And then you can imagine this is a thermovac chamber where we generate that vacuum and thermal, that minus 55 to plus 125 type of temperature conditions. So this is a big chamber, almost 10 to 12 meter diameter. And inside that we lower this, to put this satellite inside that also is a big job. So you have multiple cranes, and with that you lift that and put insert so that you don't damage anything. That also is to be taken into account. And almost no space was available for other people to move. Normally all the satellites are small, so chamber has been designed keeping your maximum satellite size in mind. But in this particular case, almost it was meeting the total requirement itself was just bare enough to test my satellite. And this was how inside again, after lowering it, we have to deploy this antenna and then test all this. Now in the one, I can relate one anecdote about this. When we were testing this, it was working very well at higher temperatures. But as I go below, say, minus 15 degrees centigrade towards minus 10 or minus 5, it started giving wrong signals. Now, there is nobody inside the chamber because all measurements or monitoring is done outside the chamber. The chamber is closed to generate the thermal and vacuum conditions. Now, sitting outside from the signature or the data which we are getting from this satellite or payload, I have to decide now which system could have been in problem. And as I mentioned, there are 1400 subsystems sitting there, 314 microprocessor, and there are other RF systems. So total around 1400 to 1500 modules are there, electronic modules. Like in your PC, you have some 4 or 5 cards are there. Now I have 1500 cards sitting there. And sitting outside from the signature which I am getting, I have to find out where could be the problem. And this problem doesn't occur continuously. It works very fine above minus 15 degrees centigrade, but as I lower the temperature, there is problems start coming up. So that was a big major effort on our part to do analyze. And then this chamber, every day you spend some 5 lakh rupees to just pump that liquid nitrogen to generate the thermo-vacuum conditions. So it is a 15 to 20 days job. Total testing requirement lasts up to 20 days. I cannot stop in between also. See, one way is stop everything, bring it out, and try to debug where is the problem.